The last subject in this chapter is the mean value theorem for integrals, which I have written on the board up here. You see it has the average value in it, so that's why it's in this chapter. Now, this is mostly a theoretical result. It's not something that we're going to be using to do any problems. It's just something which may appear at some point in the future on some proof. Okay, so take from that what you will. Maybe there's a problem on it, but it isn't that important. The idea, though, is sort of makes sense. If we have a continuous function, okay, let me just say this before I go, if I read it. Let me just point out the fact that in the previous video we talked about finding the average. F does not have to be a continuous function in order to find the average. You could have some jumps, right? You could have some jumps as long as they're not infinite. If you just have some jump discontinuities, you can still do that integral, so you can still find the average. However, if f is a continuous function, like here, and I go to find the average, let's say the average value is here, well, about that, like I said here, right? You can kind of imagine why that might be the average value, because what you can see, I made this little thing here. Now, if I take this stuff that's above and that stuff below, I could like cut that off and fill that in, and it looks like it would fit, right? And similarly, there's some up and down there, same deal. So it looks like it's pretty good. So that is actually what you will have with the average. And what this theorem tells you is that if the function is continuous, at least one point, it's going to go through that value, which is the average, right? So in this case, there were 3 of them. Each of these might be a value of C. And it doesn't matter really where that value is. It's just a statement of existence, right? That value exists. So very similar to the regular mean value theorem, the mean value theorem for derivatives. And in fact, we use the mean value theorem for derivatives to prove this mean value theorem for integrals. So that's what I'm going to do. Okay? So what we're going to do to prove this we're going to use the mean value theorem, the ordinary one, with a function, but the function we're going to use is actually the function that is the antiderivative of the little f up here. Right? So, fine. Before we go on, let's write down what the mean value theorem is. It's going to be hard to fit all this on this board. So let me do this. Let me get rid of this picture and write a little box here. And in this box, I'm going to write down the regular old mean value theorem that you guys learned last semester in Calc 1. Okay? I'm going to write it with a big F because I'm going to use it with this big F. And I have a little f with something different, so I don't want to confuse myself. So for the mean value theorem, we need our function to be continuous on the closed interval AB, and we need it differentiable on the open interval AB. And if we have both of those two things, we can say, then there exists C such that f prime of C is f of B minus f of A over B minus A. right? And if you remember what this means kind of geometrically, if this is my function, big F in this case, what we're saying with this here is that if I look at the secant line between these 2 points, A, B, right? It's going to be something like this. Somewhere in here at one point, there's at least one point C where the tangent line to F has the same slope, so it is parallel. So that's what the mean value theorem is. This is the mean value somehow of the slope. So we're going to use that here to find the mean value theorem for integrals. We're just going to rewrite this. Real quick. And I know, by the way, I know I can rewrite it, but I know I can use this because from the fundamental theorem of calculus, I know that this guy is continuous and it's differentiable, right? Because its derivative is little f. So I can certainly use this mean value theorem. I can use this conclusion. I'm just going to rewrite it so this guy is on that side. So by what I know already about integrals, I can just write that down, right? Now, let's see what we have. F primed of C is just little f of C, right? Because big F is the antiderivative of little f. So that gives me this, little f primed of C. And what about this? Let me just put A and B in for x there. So this is going to be A to B of f of x dx minus A to A of f of x, t. I mean, it doesn't matter, but it's good to be consistent, right? Because we had x up here, so that's why we were using t. Okay, but this guy is just 0, right? Because it's an integral from A to A. It's not going anywhere. And then I'm done. See, wasn't that easy? Huh. Because this is actually what I want to conclude, right? This is the same thing as up here, only this b minus I is up there. So very easy little proof. Direct consequence of the regular mean value theorem. When would you use it? Not very often. I'll tell you that. Not very often at all.